Today's program is detailing load-bearing concrete masonry. Here are the learning objectives along with the description. The continuing education, you'll receive your T8 if you're an engineer, or you will receive one learning unit health safety welfare credit as well, provided by MISL. We will have a couple giveaways today, a couple code books for 60216. You'll see a little plastic box shortly making its way through. It will eventually make its way up front for the giveaway. That'd be wonderful. If you don't have a business card, just go ahead and tear off a piece of paper and throw it in there and maybe you can. There will be a test on Monday if you do win. Our sponsor is Best Block, committed to serving specifiers, contractors, and installers across the country. We have Diana Johnson here. Diana, would you like to say a word? Thank you, Diana. So then today's speaker is Jason Thompson. Jason Thompson is the president of Coltivomae, a multidisciplinary firm located in North Virginia. Prior to founding Coltivomae, Jason worked for the National Concrete Masonry Association for over 25 years after previously working at a private engineering consulting firm in Washington State. Jason's duties and responsibilities over his career span an array of activities, including design, construction management, research and development, codes and standards advocacy, development of design tools and resources, and delivering seminars and lectures covering these subjects. Jason has served in several leadership and executive capabilities, including chair of the Masonry Alliance for Codes and Standards, board of directors and executive committee of the Masonry Society, technical advisor to the Code Resource Support Committee, and the technical coordinating committee of the International Code Council and numerous other forums within the construction industry. Please give a warm welcome from Jason Thompson.
Thanks, Margie. Afternoon, all. So, if you guys don't want to stand, you can come up. There's plenty of room in the front row. You just got to answer questions when I ask them. So, afternoon. Before we get into any of these specifics, I did want to you guys read the description of what we'll be talking about, covering some general from a pretty high level, detailing practices, what's good, what's bad. But I want to give you guys a little bit of context as to sort of my background as it relates to what we'll be talking about. So in a previous life, one of the tasks that I did was whenever there was any sort of a disaster, and this could be an environmental disaster, earthquake, hurricane, tornado, or man-made. So, for example, like you guys may remember the West Texas fertilizer plant explosion. One of the things that I did is I went out and visited those sites and looked at the damage of the masonry structures and tried to figure out, are there better practices that we could be recommending through the industry lens, or are there changes we should be implementing into the building code to make sure those types of failures don't occur. We can't control what happens, but we can control what happens after the fact. And so I want to give that as a little bit of context, because some of the details that we're going to be going through isn't just looking at, here's how to do things, but it's also looking at slightly through the lens of what happens if we don't do things. I mean, there's a lot of standards of care back in the 40s, 50s, and 60s that were common masonry detailing, design, and construction practices that we just wouldn't use today, because we've kind of figured out they proved through use that they're not the best way to do things. So that was sort of the grounding background, if you would, genesis behind some of the details that we're going to be walking through here. And of course, you guys have handout slides and things of that nature. But, even though we sort of had the syllabus laid out in front of us, keeping things fluid, keeping things fairly flexible. Because at the end of the day, making sure you guys walk away with the information that you guys need is always the most important task of the day. So if you do have questions, absolutely any point, shout them out. If you want to, just like Mr. Albert, save them to the end. We'll save some time at the end to be able to kind of tackle those questions as well. But don't be shy about raising your hand and asking a question. If it's a hard question, I'll defer to Daryl. If it's an answer I don't know, I'll give you the code word of it depends, and we'll talk about it later kind of thing. So before we get into the specifics of details, I want to talk about bigger detail types of things. One of the biggest questions I tend to get is, all right, you got concrete block and concrete. What's the difference and why are there different codes? And we're kind of drill into some of those nuanced details. But to me, it's, my background growing up on the West Coast, started practicing, cut my teeth on the Uniform Building Code on the West Coast. For me, detailing practices for masonry were always centered around reinforcing steel, right? It was UBC country, it was higher seismic or high seismic. And as a result, the concepts around unreinforced masonry just were kind of foreign to me until I moved to the East Coast and started seeing some of those requirements. But when we look at it through the lens of concrete masonry versus concrete, they're both basically concrete, right? It's cement, aggregate, water mixed together. Really, the only kind of material difference is all concrete block is dry cast, whereas pretty much everything under the concrete umbrella, reinforced concrete umbrella, if you would, is a wet cast. And we could end up incorporating design provisions into a single standard that would address both, with simply just kind of introducing different types of coefficients or modifications that would apply to specifically dry cast concrete or wet cast concrete. We kind of understand that that's true. But when you look at it from the reinforcing detailing practices, they are a little bit different in terms of when we're drafting up or when we're incorporating design requirements for masonry, we know that there's limitations in terms of practical and feasibility construction practices that apply to masonry that don't necessarily apply to concrete. And so that to me is kind of one of the underpinning reasons why we have different standards and different detailing practices between masonry and concrete, is because we just can't do some of the same types of details in concrete block that we can do with reinforced concrete. So with concrete masonry, we're really kind of fundamentally limited to that vertical and horizontal grid. It doesn't mean that we can't do different types of things, and by and large, the TMS 402 doesn't prohibit doing things like what you see up on the screen. We just sort of recognize that they're not all that practical, they're not all that feasible through the lens of masonry construction. So we tend to, as we draft up the provisions that are now included in the TMS 402, we have that sort of implicitly buried into a lot of the discussion of, yeah, we could do certain things, but it's really hard to execute some of those types of details out in the field, like what you have for reinforced concrete. Because you're dealing with, a concrete block. It's basically a stay-in-place form that's also a structural component of the overall assembly. So again, it's not that you can't do things like tying your vertical reinforcing steel within a masonry wall. It's just not always practical to do so. And so we sort of work that into some of the implicit detailing requirements that are stipulated through TMS 402, as well as some of the industry recommendations. So I did want to kind of set that as sort of some grounding criteria as we looked at some of these details. It's not to say that you can't do things even better than what the industry practices are or what TMS 402 would require. It's that there are some limitations that we have with masonry construction that you don't necessarily see with reinforced concrete, even though fundamentally they're the same material. We just put them together in a slightly different way and they get detailed as such moving forward. So before we get into some of the things, I did want to at least give a shout out to a few of the different organizations that I'm stealing some of their resources on. But if there's always one big takeaway is, if there are resources that are out there that you guys aren't familiar with, you can always go back to the office and use those or mine those resources as much as possible. Obviously, the big one, if you guys do much concrete masonry design, is the National Concrete Masonry Association, which, if you haven't heard, is now called CMHA, or Concrete Masonry Hardscapes and Hardscapes Association. So pretty much everything's still branded NCMA, because that's just rebranding just literally occurred. So you'll probably start seeing less and less NCMA and more CMHA moving forward. But they've got a ton of resources, obviously, that are all free to access online. In terms of detailing, the one that I would probably say is the most comprehensive is their annotated design and construction details. And this one has hundreds and hundreds of CAD-based, vector-based drawings that you can, again, download and apply. As with any of these details that we're going to be talking about, they, again, are pretty high level. They don't get into very, very specifics on project-by-project basis, because obviously they're not intended to do those types of things. The next organization is the International Masonry Institute. So you guys may have heard of this group. Now, I bring them up because their details are not vector or CAD based. They do SolidWorks. They do SketchUp types of things, which I find an advantage from an instructional or teaching perspective when I'm working with younger engineers, because you can go in and look at some of these three-dimensional drawings at lots of different angles, right? So if you're ever kind of curious as to how to do a connection or how to meld two different types of materials together, you can rotate things around to be able to look at it in a lot of different views, to be able to kind of get a gist or an idea of how to apply it to one of your specific details. And then the third one, which you may not have heard of because it is actually north of us from Canada, is the Masonry Institute of British Columbia. They've got a big database very similar to what IMI has. They are all solids based. They're developed in SketchUp. The one thing I do like about what they have is really kind of what you see up here on the top is their navigation tool. So the way that they've sort of put together their library of databases is they give you a building, and then they give you places that you can click on throughout that whole building, and it will pull up details appropriate to those, whether it's cross sections or details at roof floor levels, what have you. So it's just a lot of the same types of details, but also just a different way to kind of interact with it. So depending upon what you guys use in your offices, whether it's a CAD base, whether it's a Revit base, there's some different types of resources that are out there. Now, having said that, as we kind of go through some of these things, I'm actually going to pull up some of their details and sort of pick them apart as well. So recognizing that there's lots of different ways to do things, and some of the details that are out there as kind of industry practice don't always address every little thing. So some of those nuances are good examples for us to be able to talk through here this afternoon. So we all know the location. What I'm going to be focusing on is really the connection component of our load path as it applies to detailing our masonry structures. So I'm going to kind of start it and kind of lump it into a few different categories. I'm going to look at that base component, that base connection where that masonry wall connects into the footer or the foundation below. Then kind of work our way up the wall, look at, in terms of tolerance placement requirements for the reinforcing steel. So not a lot there, but a couple of nuanced things to discuss. And then finally, the connection at either the roof or the floor level. So these are kind of the three areas that we'll focus on here over the next few slides as we look at maintaining that load path, ensuring our connections are stable, there, verified, everything else. So starting with our base, the two primary things I'm going to talk about in terms of their implications on detailing is obviously how we interface or how we connect to the footer itself. And then obviously, because it's the base of the wall, and the footer to wall tends to be that transition between trades, right? You got a concrete sub versus a mason sub, installing the two. That tends to be one of those areas where you have lap splices or mechanical splices or welded splices or some kind of splicing to maintain that tension tie within your masonry wall. So starting with that connection, that dowel at the base, a couple of key things that I tend to see, and again, this kind of gets back to, sometimes it just tends to be a trade coordination thing more than anything else. That concrete contractors installing the footer, the mason contractor comes in after the fact, they have to work with the dowels that are existing. One thing I do tend to see a fair amount is what contractors occasionally call wet sticking. So they place the grout, they place the concrete, and they come in after the fact, and then they place the reinforcing steel. So there's really no code, whether it's a concrete code or a masonry code, that allows for that type of construction practice. And I get why, it's a little bit easier to be able to do because you got the concrete already placed. Once it starts to stiffen up, you can drop a rebar in there, and it kind of stays in generally that position that you apply it. You can't really tell from the top picture so much. And this isn't actually a building. This is actually a site fence around a residential property. But what they ended up doing here wasn't even wet sticking. They had the steel in place before the footer, but the way they placed the steel was just a straight bar, and they took a hammer and they driven it into the ground, and then they placed the concrete around it. So luckily, this is in Arizona, so they don't have a whole lot of moisture, and so this contractor said he's been doing this like this for 50 years, and so it must be right? But, it's Arizona, it's fairly dry. I'm assuming they're probably not getting a whole lot of corrosion issues with that rebar that's actually buried in dirt, not in the concrete itself. But obviously not a good construction practice. We've got to maintain our cover distances around that footer steel, just like what we do with the exposed above grade wall as well. The bottom picture shows a little bit more of that wet sticking. So this was a situation where they came in after the fact, and all that little toothing that you end up seeing there, that's where they came in and placed the hook on the bar into the footer itself. Placement tolerance is obviously one of those things that you got to worry about as well. A couple extreme examples. One is I kind of put it into the I don't care category. The other one, obviously, they just had some formwork movement that ends up misaligning those dowels. We'll talk about some details at the end because this stuff does happen. And so when you run across these types of situations, TMS 402-602 for masonry does have some allowances for how to realign things once things are set and in place, specifically looking at those dowels coming up out of a footer or foundation into the masonry wall. So with our load path, it obviously all starts with the foundation. That's where we're going to start. We're going to move all the way up to the top of the wall. So ensuring that that connection is going to be, kind of a critical part for us. So for the lap splices themselves, as I sort of alluded to before, we can for splicing in general, we can lap splice, we can do mechanical splicing, and we can do welding. Now for masonry construction, all three of these are permitted options in TMS 402-602. Welding's not all that common. Mostly it's an access issue, right? Because your steel is already inside of the masonry wall, even if they haven't grouted that wall, getting access to that reinforcing steel to weld two rebars together tends to be a little bit complicated, but it is a permitted option. The only caveat on the welding, I won't talk a lot about it, but if you do weld the reinforcing steel, there is a requirement that you have to use an A706 rebar, because otherwise you can potentially embrittle the reinforcing steel. You don't get the strength or ductility out of it with the lower alloy steels. For the mechanical splices, they are certainly an option. They tend to be a little bit more expensive depending upon how much steel you're reducing by removing the laps. Sometimes it's a good choice for reducing congestion within your cells. The one caveat on the mechanical splices is there's a lot of different types, and just like with concrete, masonry has a lot of different types of rebar splices, some of which are not necessarily what I classify as a structural mechanical connection. They will tie two bars together, but they may not develop the full yield strength of the reinforcing steel. They may not develop 125% or 140% of the reinforcing steel. So do pay attention depending upon what type of mechanical splice. They're just rated for different types of load transfer depending upon their intended application. What I'm going to focus more on is the lap splicing side of the equation. So we got a dowel that comes up out of the footer, and it's going to be lapped with the vertical bar in the wall. Now, years and years ago, if you guys have been practicing long enough, TMS used to have a requirement that basically said for masonry, we lap our reinforcing bars 48 bar diameters. Really easy to apply. Everyone remembered it. It didn't change a whole lot depending upon all the variables that can come into a project. But we also sort of recognized it wasn't the best solution because it doesn't take into account things like strength of masonry. We know strength of masonry is going to influence the lap splice strength and performance. It doesn't take into account things like this K, this cover distance. It doesn't, which influences this lap strength and performance. So long to short, we ended up with a new design equation for lap splices going back, 15, 20 years now. That has, and I'm going to kind of refer to these gamma factors, and we're going to circle back to those gamma factors, but kind of think of these gamma factors as these are bar coefficients, if you would. As the bar size gets bigger, the lap splice has to go exponentially bigger. And we could do that with, a more complicated equation, but it was kind of a simpler way just to say, let's introduce these gamma factors. And for small bars, gamma's 1. As our bar size gets larger and larger, that gamma gets larger and larger as well. Now, relatively new is the introduction of this psi factor, this confinement factor for lap splice and development length. So in essence, what this is if you're familiar with detailing for concrete, it's a very, very similar type of detail that when we test these laps, and generally there's lots of different ways you can load reinforced masonry or reinforced concrete. You can load it in flexure. The worst case scenario is obviously we're loading our masonry elements in direct tension, right? So any lap goes into direct tension. And that's really kind of what all the testing that predicated these details, these equations was really based upon. What this confinement factor does is if we have any reinforcing steel running transverse to our laps, it will actually confine our lap and give us more strength, better performance as a result. The one issue, without getting into the nuts and bolts of running through actual calculations, when people plug numbers into this equation for this confinement factor, the psi factor, what you'll quickly notice is it gets very, very small, very, very fast. So in other words, this number, even using conventional 5, 6, 7, 8 number bars, will go to zero very, very quickly. And so a lot of times designers, when they first run through these equations, their question is I must be doing something wrong because all of a sudden my lap splice goes to zero very quickly. And that's actually kind of intended to how it's intended to work. A little bit of confining steel goes a long, long ways in terms of how these elements perform. And the best way to kind of think and visualize about this is what this confinement steel does, what this horizontal, or it could be vertical, it's just any steel that runs perpendicular to your lap. It's kind of hard to see here, but what you see on the top of the vertical bar, there's a lapped bar that starts right about there, and then there's another vertical bar that goes up. So there's the lapped bar, and then the vertical bar up, and then of course the bar on the your right hand side is the horizontal confining steel. So when we reload these laps in tension, so we're literally pulling on the laps so that we're trying to pull them apart, what we end up seeing is there's several different ways in which a lap splice could fail. We could literally neck down and yield and fracture the reinforcing steel. That's obviously not a masonry limitation, that's a steel limitation. We could literally just pull the bar straight out of the grout. So what we're left with is just kind of a smooth bored hole in the grout itself. Or more predominantly, we end up doing what's called a longitudinal split. So down the length of the lap, a crack will start to form and propagate out to the exterior surface of the masonry. And once that crack hits the exterior surface, there's no more grout confining or holding the lap splice, and so it splits apart, lets the lap go, and the lap releases, right? So at that point it fails. What the confining steel does for us is it runs perpendicular to those cracks. So as those cracks begin to propagate out from the lap, it'll come in contact with the horizontal confining reinforcing steel. It'll stop it, won't propagate any further. And so we can get away with a lot of extra strength with just a little bit of horizontal reinforcing steel, because obviously the tensile strength of steel is much, much higher than the tensile strength of concrete or masonry. What you see here on the bottom photo, that's actually looking directly down the axis of a lapped bar. So this is the end of a lapped bar, and so you can kind of see these cracks just starting to form. So this was a test specimen that was just at impending failure, showing kind of that mechanism that develops this longitudinal split. So long and short, with our confinement factor, we can add steel in. It can reduce our lap lengths, but as we'll talk about, there's pros and cons and a big caveat on where and how and where you want to actually use those details. So to give you kind of a punchline in terms of if we ran the numbers using that equation for different bar sizes, and this is all for 8-inch block centered in the cell, we have a lap length for each bar size based upon no confinement, and of course a lap length with the confining steel. So the first thing you might notice is for the small bars, the lap length goes up, which doesn't make a whole lot of sense, but it's how the math actually works out, at least for this particular scenario for 8-inch block centered in the cell. The reason is, as we'll talk about here in a second, is there's actually a minimum lap length associated with this confining steel to ensure we don't have that pull-out failure mechanism, right? We don't want to have that smooth bore just left in the masonry grout after you load up the reinforcing steel. But obviously, what you see here is after that number 5 bar, the lap splices start to get really large, really fast, right? And that's that gamma factor we talked about before kicking in. For 6s and 7s, 8s and 9s, that gamma factor starts to make those lap splices exponentially larger. And that's fundamentally really probably where, if you got really big bars or small cover distances, where confinement may potentially help. The other sort of caveats or conditions on, and this is out of the TMS 402, is for this confining steel, We can add some, and a little bit goes a long ways, but there's a limitation. There's a cap on how much confining steel we can use, how much is effective. So there's a limitation on that horizontal bar in this picture. It can't be, at least in terms of the calculations, can't be taken larger than 0.35 square inches. So if for whatever reason we had a number 9 bar in our horizontal bond beams, you could put the number 9 bar in there, but the area of steel you use in calculating the confinement effects can't exceed 0.35. And that's really sort of research-based to say at some point you just sort of cap out on how effective that confining steel is. The next requirement in terms of detailing these is the transverse offset. So this means the distance horizontally from the lapped bars to that confining steel, that horizontal distance between these, the lapped bars and the horizontal confining steel, can't be more than 1.5 inches. And if you go back to that image we were looking at before that showed the crack starting to propagate out from the lapped reinforcing steel, that's really sort of driven off of that. As that crack starts to propagate out, if it gets too far away from the lapped bars, the masonry's pretty much failed at that point before it engages that horizontal steel. So we have to keep the horizontal steel fairly close to the lapped bars in order for it to be effective. The next one down, the longitudinal offset, that basically says that from the end of the lap down 8 inches, that's where that horizontal reinforcing steel has to be placed. So we can't have it cross at any location across our lap. It has to be at the ends of the lattice place. And as I alluded to before when we looked at the numbers in that previous slide, our minimum lap length can't be less than 36 bar diameters, which is why we see things bump up for these small bars. There's that requirement of 36 dB that kicks in for these small bars, because otherwise you'd end up with something even smaller than that. And what that 36 dB is intended to preclude is that pull-out failure. We don't want a bond failure by having such a short lap length. It just basically debonds from the grout, and you're just left with a smooth bar or a smooth hole in the middle. So, oh, yes.
So we have a Maxima, a gray vehicle blocking Lindbergh driveway. Anybody know that your vehicle? Gray Maxima? All right, thank you. All right.
Speak up now, because it might not be out there when you go wrap up, right? So when we start talking about the lap splices, there's a couple of these big caveats I sort of kept alluding to. They do help. They help when you've got big bars that you're lapping. But my general recommendation is really only use them if you've already got the bond beams in your wall. In other words, if you really kind of shake through the details and the number crunching, it doesn't help a whole lot to add in extra horizontal steel to try to reduce your lap lengths a little bit. You'd end up using more horizontal steel than what you end up saving with your lap splices in the long term. And they start to become a little bit more complicated to construct. So, here's a couple of different scenarios where, we've got a dowel that comes up, it's lapped with the vertical steel, and we put in our horizontal bars, for our confinement. And if you're in a market, like St. Louis is a great market where you could have some specially reinforced horizontal or specially reinforced shear walls. It could be high seismic D, it could be moderate seismic C. And some of those detailing practices sort of shake out a little bit differently depending upon whether you're moderate or high seismic. But if we say that, this particular project is going to be partially grouted, then the mason contractor would have to stop and grout those horizontal bond beams and then come back after the fact and be able to grout that vertical steel. So it's a lot of starts and stops to the actual construction to accomplish this type of detail. Now, if you do have something that's going to be either, likely solid grouted, so either your vertical steel is very closely spaced together, so you're going to end up solid grouting this thing anyways, then you might want to look at considering incorporating those horizontal bond beams if it makes sense to be able to reduce those lap splices, because you're just going to end up solid grouting everything anyways. So it does kind of depend upon what types of applications, whether you're solid grouted, partially grouted, whether that horizontal steel in the bond beams is already there. So if you got a special reinforced shear wall, you've got bond beams every 4 foot regardless, and maybe potentially take advantage of them. So having said all that, I'm going to shift gears a little bit and talk about alternatives to all those types of things. So one of the things that we're starting to see more and more across the country is just different unit configurations. So this photo, which you saw a few slides back, that's actually California, and that's frankly kind of how they do things out in California for many, many years, right? So they've got vertical steel in virtually every cell, horizontal steel, if not in every course, maybe every other course. And so they're going to be solid grouting. And we've got a grid of reinforcing steel like that. They got to figure out different ways to be able to install the units, right? Because they're just not going to be able to work around every single part sticking up out of the ground. And so what you see out on the West Coast a lot of times is these open-ended block, right? So either one end or both ends of a block are open, and that facilitates and allows for the mason to actually thread, the bars up around the reinforcing steel, as opposed to doing something like on the upper middle where the mason's got to lift things up and over and down and really actually kind of thread things through. So I don't know if you guys are starting to see more and more of these. Maybe it's a question for Diana. If you guys see open-ended units more around here. Yes? A little bit. So there's, if you can't hear Diana, so there's actually some other benefits of reducing the number of webs, because you reduce the thermal bridging. That gives you higher R values. So there's a secondary effects associated with it. I've got it focusing on the structural side and the detailing side of things. One of the benefits I really kind of like about these reduced web units, you remove one of the webs, you open up the inside of that wall considerably. So what you see here is a couple different wall assemblies that just have the outside face shell removed. The one on the upper right, that's a typical 3-web, 2-cell unit. The one on the lower left, this is a 2-web unit. So we've just taken one of those webs out, but you can see how much more it really kind of opens things up. And from an engineering perspective, that gives me a lot more confidence in terms of when I detail and put steel in it. It's still up to the mason contractor to ensure that the grout gets placed and consolidated correctly. And having that open area to be able to do that is certainly more advantageous. There's also some other things, so Diana was also kind of reminded me, there's different types of format units that are being introduced. So everything I've got up here is all the standard, 8816. But there's, other types of unit configurations that are being introduced, like the 8832, so it's twice as long. It does require mechanical assisted, installation devices, but a lot of that technology is being introduced more and more into the field. All this stuff, all these details that we're going to be talking about, they're really sort of independent of the unit configuration. You don't design these units any differently, detail them really any differently. They're just more to facilitate the construction end of the equation more so. So staying at the base of our wall, and again, if you guys have questions, stop me, otherwise I'll just keep going. So staying at the base of our wall, and I'm going to start off by saying these are bad details, okay? So don't take pictures, don't go back and try to implement these details, okay? But I had to go some digging around. You guys may have seen these before. These are actually out of some NCMA tech notes, and if you looked online hard enough, you could probably still find them out there. But they really sort of illustrate the example that we're going to talk about next at the base of our walls, which is when we incorporate flashing at the base of our walls, what does that do to us structurally, right? So we're relying upon some sort of a stress transfer between the upper wall and the base, and if we don't have anything crossing that flashing, we've functionally just put base isolation into our walls to some degree, right? And so when you look at some of these old details from NCMA, they have these notes in there saying, wow, you got to check this out. Because there wasn't a whole lot of research or other options that are out there to definitively kind of give guidance as to how to address this type of issue. We kind of suspected there was something going on, but we didn't have good data to be able to say, here's how you actually go about fixing this issue where you've got flashing at the base of the wall. Today, we do. So we end up in, these are some old NCMA details that tried to work around really complicated ways of maintaining some sort of a load path across these flashing locations. And so I know it's kind of hard to see, but there's these stepped flashings, and you have these weird joints, and I'm sure the mason contractors love building these types of things. But long to short is this was sort of the stopgap solution until some research was available that said, how do we detail or how do we design around this confidently knowing that we still need to maintain our load path? And so back in the 2016 edition of TMS 402, so we're going back a couple cycles now, they did introduce what we refer to as shear friction provisions. So regardless of what that interface material is, there is provisions in there now for how to detail or how to design or how to check to make sure you've got enough shear transfer mechanism crossing that flashing plane. So what you see here, and it's really kind of based upon two different coefficients. I'll talk a little bit about these equations, but essentially there's a frictional coefficient that's included. It's 1 if it's concrete on concrete, basically, and it's 0.7 for pretty much everything else. That pretty much everything else is intentionally intended to be pretty much everything else, recognizing that there's lots of different types of flashing. You know, there's metal flashings and EDPMs and self-sticks and all those different types of flashings. This number is we sort of recognize as being a pretty conservative low value because we want it to apply to kind of everything. There could be some scenarios where it should be 0.8 or 0.9, but we're kind of just basically at this point saying it's 1 or pretty much everything else. Now with shear walls, so let's say for example we're checking the in-plane strength of our shear walls. There's a couple different checks depending upon this trigger, this M over VD, which you can kind of think of M over VD. M is our overturning moment, V is our shear, D is the length of our shear wall, as sort of an indirect measurement of our squatness of our shear wall. So as our shear walls get very tall and thin, but not very long, they're going to be flexurally dominated. If our shear walls are short and long, they're going to be shear dominated. So that's really kind of what M over VD is saying is for short squat walls, then we've got a shear dominated mechanism that's going to be controlled by this equation. For tall, skinny, for tall shear walls that are not very long, we end up with this flexurally dominated mechanism. And of course, we do this linear interpolation between the two. But long and short, we now got a design check. So if you are one that has always kind of questioned, wait a minute, I've got base flashing or I've got flashing incorporated into my load-bearing shear wall elements in my masonry structure, how do I ensure that I'm getting that load path? How do I ensure I get that force transfer mechanism across that flashing detail? And here's your now design check to be able to accomplish that. One other final thing is I kind of alluded to this before with the foundation dowels. If they don't get placed exactly right, there's a couple of options in TMS 602 that says you can bend, you can move things around a little bit. So basically, if you got a dowel that doesn't perfectly align with that vertical reinforcing bar or the cell that's intended to be vertically reinforced and grouted, you can bend that bar over an inch for every 6 inches of height. There is actually an option within 602 that says you can also do what's called a non-contact lap splice. So physically, those bars don't have to be in contact with one another. They can even be in adjacent cells, just not more than 8 inches apart. And this is sort of indirectly related to a question I get occasionally is, do you have to wire tie laps together? You know, so when the contractor is installing lap splices, do they have to be wire tied? The short answer is, if they have to be wire tied to maintain position for tolerance purposes, sure, wire tie them. The wire tie doesn't actually contribute much to the strength whatsoever. So we've tested with and without the wire ties. It doesn't do a whole lot in terms of adding any additional contribution to the strength or performance of the lap splice. Moving up our wall, again, the placement stuff, this one's pretty straightforward. There are tolerance requirements for where we place the reinforcing steel. This is all spelled out within TMS 602. What I really want to kind of talk about with this one is how do we accomplish these tolerances? You know, TMS essentially kind of says, here's the tolerances. We don't tell you how to do it. It's kind of deemed to be a means and methods issue through the lens of TMS. Now, in the past, there were codes like the Uniform Building Code that stipulated you have to use bar positioners every so often over the height of the wall. There's actually kind of a debate on both sides of the fence on the benefits of bar positioners. You know, certainly they do hold the bar in the correct position, right? But they also create issues with congestion and potential hang-ups for the grout as you place them. And so, you know, you can honestly talk to different engineers and architects and they have opinions on both sides of the fence, which is probably part of the reason why TMS has said, look, we'll just leave this up to a means and methods issue. So as a specifier, if you want to include the bar positioners because they make you feel comfortable, you know, I think that's fine. If you don't, you know, leave it up to the contractor. Contractor's got to figure out the means and methods end for themselves. The other kind of thing with the bar positioners is there's so many different types of bar positioners that are out there and so many different types of core configurations for block. They're not always compatible with one another. So That's something else that, the mason contractor should kind of be sorting through and figuring out. Moving on up our wall, so now we're at our connection at the floor, the roof level. And we'll start with kind of the generic stuff of anchors. And TMS 402-602, they address embedded anchors. So bent bars, headed bars, those are addressed within TMS 402 because they're generic, they're non-proprietary. If you do a fair amount of that type of design, designing anchors embedded in masonry, there is a free spreadsheet that you can download through the NCMA website. It essentially has, these are some screenshots, but the blue cells are inputs, and at the bottom, it'll just do all the calculations for you. So depending upon whether you're doing a ledger connection, top of wall connection, it'll be able to address all those types of things. Now, I personally tend to be one that gravitates a little bit more towards the post-installed anchors, at least in terms of certain types of connections. If I'm doing a wood ledger to a wall or something of that nature, as long as I can get the strength I need out of those post-installed anchors, I tend to gravitate a little bit more towards them, because with the embedded anchors, the mason's got to be installing them as they go, right? They got to be in an exact right spot, and we all know as-builts and specifieds aren't exactly always the same. So, the post-installs give you a lot more flexibility. Once things are up, they can come in, they can punch some, drill some holes in, whether you're using ledge or screw or helical or epoxy. They give you different options. They tend to be a little bit, they're proprietary, so they tend to be a little bit more expensive. But you tend to save a little bit on the labor side after the fact. And of course, you don't have to readjust things if a bolt gets embedded in the wrong spot and end up moving it down the road at some point in the future. Now, they don't work for everything, obviously, but they are a fairly good option. One thing I did want to mention, and it's not shown here, but so with the embedded anchors, there's, and I know it's really small for you guys to be able to read up there. With embedded anchors, TMS 402 has two options basically. There's headed, which is typically like an A307 steel, or bent bar, which is typically an A36 steel. If you ever run the numbers, I personally kind of stay away from the A36 steel. It's not that it's a bad steel. It's not that steel is faulty or anything of that nature. It's just a low strength steel. And so if you're going to be putting an anchor in for the exact same size of anchor and exact same embedment, you get almost twice the strength as you do with a headed bar versus the bent bar. So if you're really looking to economize on strength and performance, the headed bars tend to be the better option. So this is where I'm going to pull up some of those details I was referring to earlier on in the resources section, and talk about specifics associated with those that aren't problematic, just something to really kind of consider as you're putting together some of these details in practice. So the first one here is looking at how do we do the bearing connection of a plank to a masonry wall. And most of the details that you'll end up seeing out there do something of this nature, where the plank bears on a portion of the wall, and then you've got a SOAP or a half unit or a solid unit on the exterior to maintain the aesthetic continuity if you need that. But there's still a gap in there where the vertical reinforcing steel can be continuous. You can get grout down past it. It all works out great. The detail I want to point out with this one is really the plank or the slab height. So in these types of things, if you've got an 8-inch plank, it works really nice if you got an 8-inch tall block, right? If you got a 10-inch plank, then you end up having to come in through and notch out some of these units to get everything to kind of fit. All doable, but just something to kind of take into consideration. Masons are kind of familiar with how to do this. The one that's a little bit more problematic is on the non-bearing side of this detail. And so this is an issue where, I see them drawn, and they look great when they're drawn, right? They fit exactly into that course in that masonry wall. But we know that planks oftentimes have camber to them, right? So where you are at elevation on the ends is not where you are in elevation in the middle. And so this type of detail, I tend to say, is hard to accomplish, may not be the option for the non-bearing side of your planks, unless maybe you got a really shallow plank, a 6-inch plank or something like that, where you can work with that camber. But these types of details tend to work a little bit better if you got a ledger or something else of that nature. Kind of moving or staying at our top of wall, we're connecting, again to the roof or the floor line. is how we develop that bar. You know, a lot of that lap splicing that we talked about at the base of the wall is all to be able to develop the full strength of the reinforcing steel that we put into the masonry. We want to be able to accomplish the exact same thing at the top of the wall. So we got dowels or vertical bars that come up through the wall. How do we tie that into our roof so any wind loads or gravity loads that come in from the roof get transferred appropriately into our masonry and down through to the foundation? This is a detail that I probably see everywhere. Essentially shows that we've got a vertical bar that comes up. We've got a horizontal bond beam at the top of our wall. Those are all great and perfect. How do we connect those two? How do we make sure we've got sufficient force transfer mechanism between that vertical bar and the horizontal bond beam? Because that horizontal bond beam, this is the roof line or diaphragm, is where our core tensions are getting dumped, right? And what I oftentimes see is end up with a standard hook, which is shown here. So that standard hook, there's lots of different standard hooks. This is shown as a 90-degree standard hook. Sometimes it's the candy canes, 180 degree, just kind of hooks over that top vertical bar. But this isn't going to develop, those types of details won't develop our full strength of our reinforcing steel. So sort of the point with this one is standard hooks hook the reinforcing steel, but they don't develop the reinforcing steel. So you don't get the yield strength that you need out of that reinforcing steel. In order to do that, you actually have to extend that hook out, and it depends, length depends upon the diameter of the bar, a fair amount, maybe 12, 14 inches, to get that full development length, to get the full strength of that reinforcing steel. So any load that comes in from, whether it's coming in from the roof, the floor above, down, or up, if we got direct uplift from wind on our roof, for example, we can now fully develop that reinforcing steel, or that connection. Now the rub with these types of details is, as you start to put longer and more hooks in that top course, you're eventually going to start running out of room, right? I've seen lots of details where, you got vertical steel at 16 inches on center, and every one of those bars has a hook, one of those 90-degree hooks on it, and they're just starting to stack up in that top cell. And then, of course, you run into things like this where there's lots of other stuff we're trying to cram into those cells, right? And pretty soon that structural conduit's the only thing holding things together for us, and that doesn't work so well. So in this particular case, what I'd suggest looking at is, instead of hooking the 90 degree, and instead of just doing a little candy cane that just barely hooks over the top vertical steel, you can do some of these hairpins, right? So it gets a lot of the steel out of that top course, but the length of these hairpins are sufficient that you can get the full development out of the reinforcing steel. Because otherwise, and again, these are some photos from buildings that were constructed back in the 40s and 50s that, obviously they had a good connection between the roof and that top block, but there wasn't the load path that actually kind of continued all the way down. The last one of these connection things, which has nothing to do with kind of the structural side, but it's one I'm seeing more and more of, so I did want to at least kind of raise it here, is, and this one's actually completely unrelated to loads or structure, it's related to energy efficiency. So we're seeing, the fat wall syndrome, right? We're trying to shove more insulation into our walls. Our walls are getting thicker and thicker. And so architecturally, we're starting to see a lot of windows now starting to be attached to veneers just because of the size and thickness of walls. Veneers are not structural. There's nothing about a veneer that's able to carry the load from that window into the veneer. I mean, you could go around and come up with a detail, but the prescriptive detailing requirements for veneers in TMS and the IBC or IRC, they do not account for this type of additional load getting dumped into the veneer. Basically, veneers are, from a structural standpoint, they're our paint, right? They're just really, really thick paint. We're assuming that they carry nothing but their own weight, basically. Probably the least favorite part of this, I'm going to kind of maybe start off with the taboo thing. You guys won't like these next couple slides for the architects and engineers of the world, because this is kind of pointing out one of those things that causes some grief out in the field. When we look at, or when I typically see project specs, for control joints and their spacing and location, I mostly see a statement in the spec that says something like, provide control joints in accordance with either a reference to NCMA Tech if it's concrete block or brick, they reference a BIA Tech note if it's brick. And there's some recommendations out there, and they're fairly straightforward and easy to follow, especially the empirical stuff. It says if you're this tall on your wall, you got to have control joints so many feet apart. Here's the rub on that one, is TMS actually stipulates, I know it's kind of hard to read, that these details, these control joints, be shown on project drawings. And you oftentimes kind of think, well, why is that? It's a shrinkage related thing, it's aesthetics, isn't really all that important. The primary reason, it's kind of alluded to here in the commentary, but to give you a little bit better idea, this is a shear wall. So I took a 12-foot tall wall that's 100-foot long and ran it through 5 different scenarios with different types of control joint spacing. So essentially, with our control joints, we're incorporating these discontinuities in the horizontal length of our shear wall. So we're changing how that shear wall is going to react to in-plane load, and that's going to give us a different strength. So if we start at the top here, so our wall, it's 100-foot long, and we have no control joints, we can calculate based upon these parameter inputs, what's the in-plane shear strength per TMS 402. And you can see, if we put in control joints, per NCMA Tech, for example, we start dropping, and we start dropping more and more, the more control joints that we put in. So this is the primary reason that TMS 402 says, we want these control joints shown on the drawing so that it's a recognition that the designer took into account where they are and how they impact the in-plane strength of our structures. You'll see one nuance here at the very bottom where the strength actually went up relative to what it had before, even though we had more control joints. And this is really to sort of illustrate there's different mechanisms that control our in-plane shear strength. We're talking about like shear dominated versus flexually dominated before. This is one of those things where our shear walls are becoming so short in their length, their failure mechanisms start to change, and so we actually get different strengths out of them as a result. So this isn't a typo. It actually does increase strength a little bit by putting in more control joints. And of course, things get even more complicated if we start putting in openings and everything else. So I'm going to kind of go through these next couple slides fast. I know we're coming up on our 1 o'clock window. Detailing requirements, prescriptive, seismic detailing requirements. Long to short, as I'm sure you guys all know, as we get it into higher and higher seismic design categories, the code requires more and more reinforcing steel. And it's really all tied to the ASCE 7 response modification factors, their C sub Ds or omega factors for those different types of systems. They're all sort of benchmarked off of, if we provide the minimum reinforcing steel for an ordinary reinforced shear wall or intermediate reinforced shear wall or special reinforced shear wall, they're all sort of tied back to those response modification factors, those seismic coefficients that we use to either increase our displacement or decrease our design loads accordingly, because we're assuming that we get some energy dissipation out of those different reinforcement schedules. So going back to where we sort of started, minding our details is always sort of the important thing, right? Make sure you get in the right truck. They always say that, whenever I pull up my Uber app, it's always make sure you get into the right car. So let me see if I can pull this up real quick, because I know we got 1 more minute. So you guys don't need to listen to it. As soon as it gets going here, I'm going to hit pause and give you guys just a little bit of context. So if you guys, I'm sure you guys have all seen like the car crash test, right? The Institute for Highway Safety. It's actually the insurance industry that goes out and buys cars and crashes them. And their whole purpose is to try to motivate the car industry to make, safer cars. They've got a similar facility down in South Carolina that does basically the same thing for buildings. It's called the Institute for Business and Home Safety. It's funded by the insurance industry. And they've got this massive facility that can literally generate on full-scale structures hurricane force winds. And they can throw fire at it, and they can do all kinds of cool things. So if you guys ever get down there, it's always worth kind of a pass. It's by absolutely nothing, so I'm not sure why you'd ever be down there. But if you do find yourself driving through the backwoods of South Carolina, it's probably not too far away. So the context on this one, obviously 2 concrete block buildings. The first one that's called common, the other one called stronger. Which one do you think is stronger? So the terms here are really through the lens of the insurance industry. The common means common buildings that they're currently insuring, right? So these are buildings built in think of how many hundreds of millions of square feet of block buildings, industrial block buildings are out there, built in the 40s and 50s and 60s and so on. And what they really wanted to illustrate here is common, what's out there in terms of the old building stock, versus stronger, which is if we design and detail it today, how do these two structures perform? And fundamentally, the big difference between these two all had to deal with our load path, maintaining sort of that connection from the roof all the way down. So I'm going to hit start here. It's not very long. It's only 30 seconds or 47 seconds. You're going to see it fail. It's going to fail fairly quickly. Don't panic. It's going to show it again in slow motion after it kind of wraps up. But to me, I think this shows kind of perfectly sort of the mechanisms that cause some of our failures. So what you saw here is the roof obviously started to lift up. The only thing that was really kind of holding that sidewall in place was whatever gravity load that was sort of bearing down on it from the roof. Once that was lifted up, the wall just sort of fell out, right? So this will go in a little bit more slower motion. What you'll also notice here is, it's kind of maybe hard to see, but the windows and door were broken out. So they intentionally wanted to get wind inside of the building to lift the roof up and create that sort of mechanism. I always grew up with that wives' tale. I don't know if you guys ever heard that, but if big wind event's coming, open all the doors and windows, right? Let the wind just blow right through, which is exact opposite of what you want to do. It's not how we design structures. So I think with that, this is my last little placeholder. It has absolutely nothing to do with details. It's just TMS has now just published a recent new publication for dry stack masonry. So designed and constructed exactly like concrete masonry. It's just very little mortar involved. And with that, a few shout outs for people I stole stuff from, and we're at the end. So